So if you're building enterprise systems right now, I mean, you know you have this underlying fear that you're just handing the keys over to a complete black box.
Oh, the $47,000 fear. Yeah. Imagine waking up on a Tuesday, checking your cloud dashboard, and realizing an AI agent you deployed just to automate some data entry got stuck in an infinite loop.
Just sitting there hallucinating.
Right. Talking to itself and burning through 47 grand of your company's money in just 11 days. That is a real documented fintech incident from the research stack we're diving into today.
Which is terrifying. And it perfectly frames the central architectural truth we need to establish for this deep dive.
Yeah, because trusting a non-deterministic model to just figure it out in production is permanently etched at the very top of my failure spreadsheet.
I love that you actually maintain a spreadsheet for that.
I update it monthly. That's a necessary therapy exercise for my operations team.
Well, the core issue there is that a production agentic harness is not some magical AI framework. It is fundamentally a distributed systems problem. It's just wearing an AI costume.
Wearing an AI costume, I like that, because the LLM itself, I mean, it is just an RPC call, a very slow, extremely expensive RPC call.
Yes, exactly. And completely unpredictable. You're pausing your system, sending a request over the internet to a massive server farm, and just hoping it sends back a coherent string of text.
They're literally relying on complex probabilistic math for a simple workflow.
Right. Trust isn't something the model just gives you out of the box. Trust is built by creating a deterministic skeleton, what we'd call the trust harness, that quarantines that non-deterministic LLM into the absolute smallest possible blast radius.
You have to push all the reliable logic to the edges of the system. I'd argue that's the only rational way to operate, because perfect solutions simply don't exist here.
You really don't?
If you think your model won't fail, you just haven't put it in front of real users yet. The only way to build trust with your customers and, your finance department is to plan for failure at every single boundary layer.
Honestly, the only way I can even make sense of these failure structures is by mapping them out visually. I have to draw the system boundaries, the state transitions.
You and your diagrams.
Look, I can't think without them. I actually drew a flowchart of my morning coffee routine once, just to optimize the parallel processing of brewing and toasting. My partner is still not convinced it was necessary.
I would absolutely ask for the formal post-mortem on that routine if the toast burned.
Fair enough, fair enough.
But to build that trust harness you're drawing up, you first have to control how the system is defined, right?
Yeah.
Like what it's allowed to remember.
Yeah, the configuration and the memory.
And if we look at my failure spreadsheet, schema evolution has its own dedicated, very depressing tab.
Oh, the schema evolution trap. That is where so many teams just bleed engineering hours.
It is a total disaster. Let's say your system has been running smoothly for 6 months. Then a product manager decides your agent needs to collect the user's zip code before proceeding.
Just a simple required field addition.
Right. So an engineer adds zip code as a required field in your agent state schema. If you don't have migration validators in place from day 0, what happens?
Everything breaks.
Instantly. Your application boots up, reads the millions of persistent state blobs sitting in your database from the last 6 months, realizes none of them have a zip code, and just crashes.
Every single cached config invalidated over like an 8-character addition.
The whole thing comes down.
And let's not forget the terrifying reality of the Norway problem.
Oh man, that one still haunts me.
For those who haven't hit this wall yet, it's when you put the 2-letter country code for Norway, capital N, capital O, into a declarative YAML config file.
And the YAML parser uses aggressive type coercion. It sees the word no and says, this developer clearly meant the Boolean value false.
Suddenly, your routing logic is completely broken in production, and you're spending your entire weekend trying to figure out why traffic to Northern Europe is mysteriously failing.
This is exactly why the failure mode of almost every enterprise team is trying to force a single configuration format to do absolutely everything. You just can't.
No, you can't. If we look at the structural design, the correct configuration model is a 3-tier hybrid. You map it by 2 things: rate of change and blast radius.
Okay, break down the mechanics of that separation for me. How does that look in the code base?
So tier 1 is your structural contracts. This is pure code, Pydantic and Python or TypeScript interfaces. It's for your agent definitions and tool schemas.
So changing that requires a full deployment.
Exactly, a full deployment and an exhaustive test suite, because the blast radius is your entire application. Then tier 2 is your declarative YAML.
Those are the human readable tunables, right? Like prompt templates, temperature settings.
Retry budgets, yeah. But here is the critical mechanism. This YAML must be programmatically validated against your Tier 1 Pydantic schema before it ever loads into memory.
Oh, so the code essentially acts as a bouncer for the YAML files.
That's a great way to put it. And then Tier 3 is your version Postgres database. This is for hot swappable values like routing weights or instant kill switches.
Things you need to change at 3 in the morning without running a massive deployment pipeline.
Exactly. But even if you perfectly configure that 3-tier system, you're immediately going to hit the dominating physical constraint of these models, which is context rot.
Ah, yes. The massive industry myth that more tokens means a smarter agent.
It is completely backwards. The underlying transformer attention mechanism is O of n squared, meaning for every word you add to the prompt, the model's processing effort doesn't just double, it quadruples.
Right. It becomes exponentially harder for the agent to actually remember what you asked it to do.
Giving an agent more tokens actively makes it worse at reasoning. Context management isn't just about avoiding API limits. It is fundamentally a cache eviction problem.
I always explain it like trying to cook a massive Thanksgiving dinner on a tiny cutting board. You keep adding ingredients, you keep chopping, and eventually the turkey just falls off the edge onto the floor.
That is a perfect analogy.
And yet teams treat the context window like it's free real estate.
I've actually drawn literal flowcharts for engineering teams, mapping out standard CPU cache line rearrangement just to convince them to stop hoarding tokens.
Of course, you drew a flowchart for that.
It works. You have to build a tiered eviction ladder. Take Claude Code as an example. It uses 5 escalating tiers. You start with zero-cost LRU truncation.
Which just means dropping the oldest, lowest value messages from the chat history.
Right. Just simple truncation. Then you move up to adaptive replacement. And if things get really desperate, you hit tier 4, which is a blocking, lossy summarization.
Where it pauses everything just to compress the history?
Yeah, it actually forks a completely new LLM call to read the history and summarize it mid-task, which is incredibly dangerous because the model can hallucinate the summary right when you need absolute precision.
I laugh every time I hear teams talk about state management because I have another tab on my failure spreadsheet dedicated purely to times a vector database was used for the wrong reason.
Oh, let me guess. They read a few tutorials and assume, I'm building AI, which means I need a vector DB for everything.
Yes. They try to shove all 3 psychological substrates of memory working, semantic, and episodic into something like PG vector.
Let's ground this in pragmatic reality for anyone building this right now. A vector database does not have robust transactional guarantees.
Exactly. If 2 distinct agents try to update the exact same working state at the exact same millisecond, a vector database doesn't know how to queue them up safely. It just corrupts the data.
Redis is for your working scratchpad state. It's ephemeral, it's microsecond fast. Postgres is for your structural truth, forming an orderly line for transactions.
And vector databases are only for episodic similarity recall. Like searching for, hey, remember that one time we solved a similar bug?
Right. It's a complete mismatch of the database architecture to the actual needs of the system. But let's follow the data flow further down the line.
Okay.
Once your agent has its rules and its memory partitioned correctly, it has to actually interact with the outside world. It needs tools.
Which is terrifying, because handing in LLM tools is the single largest security vulnerability in the enterprise right now.
Yep. The Open Worldwide Application Security Project SWASP literally ranks prompt injection as the #1 vulnerability. That's LLM-01.2025.
And we really need to explain why it's #1. It's because trusted instructions, like your carefully crafted system prompt, and untrusted data, like a random customer email the agent just opened, share the exact same token stream.
The model physically cannot tell the difference between, here's my instruction and here's an email I'm reading that contains a malicious instruction telling me to ignore you.
It's the equivalent of classic SQL injection from the late 90s, but at a semantic level where there are no prepared statements to save you.
And the threat gets even more complex with supply chain attacks. Look at the MC Poison vulnerability.
Oh, the model context protocol issue.
Right. With MCP, the descriptions of your tools are actually passed to the LLM as part of the prompt. Attackers figured out they could swap the underlying command of an approved config key post-approval.
So the agent blindly trusts the tool name because it looks official, but the payload underneath has been completely rug pulled.
Exactly. This is where organizational psychology and system architecture collide. We keep trying to solve a structural trust problem with behavioral prompting, telling the model, please don't listen to bad instructions.
Which never works.
You cannot defend against this at the prompt layer. It requires architectural privilege separation. You need what research outlined as the dual LLM or camel pattern.
Wait, so if I'm building this, am I basically putting one agent in a padded room with the untrusted data and giving a completely different agent the actual keyboard?
That is a perfect way to visualize it. You split the persona, you have a privileged planner LLM. This agent holds the tools, it has the keys to your database, but it is architecturally quarantined from ever seeing raw, untrusted data.
Okay, and the second one?
You have a secondary quarantined LLM. This one's only job is to process the untrusted data, the external web pages, the user emails, but it holds zero tools.
Uh-huh. So if it gets prompt injected and turns malicious, it doesn't matter because it has no arms or legs. It can't actually do anything.
Precisely. The camel implementation of this solves 77% of standard security benchmark tasks with provable isolation.
That solves the agent layer subversion, but I have to push back heavily on how teams handle the execution side of things.
What are you seeing out there?
I see engineering teams using shared kernel Docker containers to run the untrusted Python code these agents generate, and it is a complete disaster waiting to happen.
Because they assume spinning up a Docker container means they are fully sandboxed.
Yes. They pass the LMS code in, run it, and think they're perfectly safe. Docker and Runk are dead for this use case. They use a shared kernel.
Which means the container still talks to the host computer's core brain.
Exactly. If the AI writes a malicious script that tricks that kernel, it breaks out of the container completely.
It means the attacker now has full access to your host machine's environment variables, your AWS keys, your entire infrastructure.
Everything. If you are executing untrusted LLM code, you absolutely must use hardware virtualization. You need Firecracker microVMs.
They do have about 125 millisecond cold start, so latency is a factor.
True. But it provides actual hardware-level isolation. It literally spins up a fake motherboard and CPU. There's physically no path back to your host machine. Or you use gvisor to strictly intercept the system calls, but under no circumstances do you use standard Docker.
It comes back to the core thesis, pushing determinism to the edges. A Firecracker microVM is a deterministic, hard physical boundary. But here is the reality we have to face. Even with safe tools, hardware isolation, and perfect configuration, the non-deterministic core will eventually fail. It will hallucinate or it will just get confused.
And it leads us right back to our $47,000 nightmare, the runaway loop.
The dreaded loop.
I actively despise the myth of agentic self-correction. You see these frameworks constantly promising that if the agent makes a mistake, it will just evaluate its own output, reflect on its errors, and fix them. It is a fairy tale.
The data thoroughly backs you up on that. React agents enter infinite loops in 40% of scenarios where they violate a physical or logical constraint.
4%.
And in those loops, they have a 0% correction rate if there is no deterministic controller stepping in to stop them.
Because a probabilistic agent grading another probabilistic agent is not a control system. It's just two people hallucinating in an echo chamber. And you are paying the API provider per token for the privilege of watching them spin.
From a systems architecture perspective, this is why you absolutely need a durable execution substrate. Think temporal or line-graph checkpointers.
How does that contract work in practice?
The contract you make with the system is strict. The orchestration and the workflow logic are 100% deterministic and replay safe. The activities, meaning the LLM inferences and the actual tool calls, are non-deterministic, but they are retried idempotently.
Let's clarify idempotent for a second for anyone newer to this. It means if the system crashes mid-thought, it doesn't run the credit card charge tool twice when it reboots. It remembers exactly where it left off.
Exactly, but I'll push the architecture a step further. I strongly argue for a strict neurosymbolic finite state machine, an FSM, that sits above the agent.
Okay, getting into the theory here.
It explicitly dictates the allowed state transitions. If the LLM tries to transition from drafting to publishing without passing through the deterministic validation state, the FSM hard blocks the trajectory and overrides the model completely.
Look, the theory of a neurosymbolic FSM sounds beautiful on a whiteboard, but let's ground this in harsh reality. FSMs get incredibly brittle to maintain when your application actually scales.
They can get complex, yes.
Before you even attempt to build an FSM, what you really need are hard budgets. I'm talking retry budgets, token budgets, and most importantly, wall clock budgets.
Wall clock meaning the total physical time elapsed since the task started.
Yes. I added wall clock budgets to our mandatory postmortem templates after learning this the hard way.
What happened?
An agent gets stuck, it spins, the API latency creeps up, and suddenly an async background job has been running for 6 hours. Escalating to a human is a valid architectural strategy. Spinning forever is not.
That's a crucial reality check.
You need a circuit breaker that says, you have been thinking about this for 45 seconds.
Yeah.
Stop, cut the power, escalate.
I actually completely agree with that. The FSM provides the logical structure, but the circuit breaker is the physics. It enforces the physical limits.
Okay, so I set up this beautiful circuit breaker. It cuts the power when the agent spins. But I have a new problem. How do I know it tripped because of a bug in my code, or because a model provider silently tweaked their model weights overnight?
Ah, the silent wait update.
This is the silent killer. I've documented this exact scenario. A major provider updates their backend. They don't change the model name, just a minor background tweak.
And suddenly the behavior drifts.
Drifts. Your agent's tool selection accuracy drops from 91% to 71%. And you only find out on Friday afternoon because your customers are flooding the support queue complaining that the AI is broken.
Which means your observability was entirely reactive. If we look at the structural solution, the industry has finally converged on the OpenTelemetry GenAI semantic conventions, specifically version 1.42.0.
Why that version specifically?
Because it gives us a standardized wire format. But the paradigm shift here is that the unit of debugging is no longer a single API call. We are moving from logging, did this function run, to logging, what was the psychological train of thought this agent just went down? The unit of debugging is the trajectory.
The entire span tree of the interaction.
Right. The invoke agent span, branching into the chat spans, branching into the execute pool spans. Let me ask you a question, because you've operated traditional infrastructure for years.
Sure.
In a normal microservice architecture, an HTTP 200 response means success, right?
Usually, yes. It means a server received and processed the request.
What does an HTTP 200 mean for an agentic system?
It means absolutely nothing. An HTTP 200 from an LLM API can effortlessly hide a completely hallucinated, catastrophic decision that it just confidently delivered to your user. Just means the API didn't crash while generating the garbage.
Which completely breaks traditional monitoring. Your dashboard shows a sea of healthy green check marks while your agent is actively draining a client's bank account. You need semantic telemetry.
And this is why pre-deploy evaluation gates aren't enough anymore. You test 200 golden cases in your CI pipeline, it passes, you deploy. Great. But what about that silent wait update on Friday? You must have a closed loop of continuous production evaluation.
But how are you layering the economics of that continuous evil? Because running an LLM as a judge on every single production trace will bankrupt you faster than the runaway loop itself.
Layered economics is the only way to survive it. You run 100% of your production traffic through deterministic checks.
The cheap stuff.
Exactly. Cheap, fast Python-level assertions. Format checks, schema validations, basic latency thresholds. Then you sample 5 to 10% of that live traffic and run it through your LLM as a judge. That's your medium cost.
And you validate that judge against human labels to watch for position bias, where the model just favors whichever answer was presented first.
Always. Finally, you take 2 to 5% of the most uncertain traces, those weird edge cases, and you pay for expensive human annotation. But here is the critical closed-loop part. You automatically take those labeled failures and convert them into new regression cases for your golden set. Your test suite has to grow weekly based on actual production failures.
It's an immune system. Your system is constantly adapting to the novel ways the non-deterministic core finds to fail.
If you aren't doing that, you aren't doing engineering. You're just gambling with API keys.
Let's pull this all together. If there is one structural philosophy to take away from this deep dive, it's this. Do not build a framework that merely wraps the LLM.
Yes.
You must build a deterministic, durable execution orchestrator. You treat the LLM as a fallible, untrusted, tightly metered activity. You isolate your config by blast radius. You brutally evict tokens from the context window to prevent rot. You quarantine untrusted data with a dual LLM pattern. And you monitor the semantic trajectory, not just the HTTP status.
That is the reality check every team needs. And I want to leave you with one final thought, something that really cuts through the current hype cycle. The multi-agent illusion.
This is a vital point to end on.
Everyone right now is obsessed with building multi-agent swarms. And yes, the orchestrator worker pattern provides fantastic context isolation. The lead agent delegates, the worker gets a fresh, clean context window, and it prevents state corruption.
Sounds great on paper.
But here is the harsh reality from Anthropic's own internal research. A multi-agent system burns roughly 15 times the tokens of a single chat.
15 times the cost and processing overhead.
For 15. And their research shows that token usage alone explains 80% of the performance variance in these systems.
Wow.
Think about what that really means. Are you building a complex swarm of specialized agents because it's genuinely necessary for your architecture? Or are you just throwing massive amounts of brute force tokens at a problem to compensate for the fact that you lack a deterministic trust harness?
It's the ultimate brute force masquerading as elegance.
It is. So before your next deploy, look closely at your own architecture's blast radius. Are you managing complexity or are you just multiplying it? Take a hard look at your state, your tool isolation, and your retry budgets. Because out in the real world, an HTTP 200 won't save you when the agent decides to go for a spin.